In this next section, 29.4, we're going to look at subsection A, talk about something called the Kuiper Belt Objects, from which it is believed comets come from. Comets orbit the sun in very long ellipses. So as we saw before, the planets having an elliptical movement, these guys are really drawn out. In the 50s, Dutch astronomer John Oort, which what I'm going to say now has not been verified to exist even as of this date, that these objects enter our solar system due to a passing star's strong gravitational perturbation or wobbling that dislodges the materials there from a very distant spherical zone at the far reaches of our solar system, somewhere between 2,000 and 200,000 astronomical units out. And this zone is called the Oort cloud. Now, touch base here, the Voyagers 1 and 2 have already passed through this cloud, and information coming back from them yet has not even confirmed this. So you have an image here of this spherical cloud where they're perturbated or knocked out of orbit and then start making their elliptical movements through our solar system. At about the same time, it was also theorized by him that these comets were dirty snowballs of rock and ice. In fact, middle school kids probably make this sort of thing with dirt and ice and push together as their model to make a comet. Here's a picture of one. They have a big chunk of ice and saying, basically, this is what comets look like. But the European Space Agency's Rosetta mission found out, and has since been verified by other missions by the United States and Japan, that comets are anything but dirty snowballs. Instead, they're very desiccated. That's a term for dry. The only water they found have been the microscopic trace amounts within the ion tail due to electromagnetic activity. This is a picture of the Rosetta mission. Since they were expecting this dirty snowball, the Rosetta lander had harpoons with explosive warheads in them to help them anchor to the surface. That was their idea. These harpoons are going to fire charges in there and keep this thing anchored to this ice ball. But instead, it was hard rock. There's no ice. The harpoons ricocheted off the surface, and the lander itself bounced off the surface and skidded up against a rock cliff and tipped on its side. This is where the impact zone was, and it skidded and it wound up underneath this shelf here inside the red box on its side. So that's how far it skidded across the surface. And more close-ups of this desiccated comets. This is Comet Hartley 2. You see here, it almost looks like a dog bone. Here's a close-up as you get closer to it. There's rocks, there's even sand dunes on here. That's Comet 67P. This is Comet Fabian. So it shows the image here and then bring in close. It's not snowballs. That's Temple 1. So these are 4 comets that either have orbiters on or would put landers on. Comets do have subcomponents or parts. This much we do know. It has a core or a nucleus. Most of the mass of the comet is comprised of rocks, organic compounds, inorganic compounds, iodized metals, and some frozen gases. And that would be the core or the nucleus we show here. It has a coma. It's a near spherical cloud of gas and dust particles. Mostly of these are volatile hydrocarbons. It means they easily go to a gas phase. And they surround the nucleus. And that area would be the coma. There's also a dust tail that trails away from the coma, and these things go up to millions of kilometers, and they're made up mostly of finer, lower molar mass hydrocarbons. That's carbon with hydrogens on them, and silicate, the silicon, the element, dust particles, and these light up from the sun's reflectance, and they point away from it, as does the ion tail that we'll note below. So those guys all point away. The ion tail can be visible, but it's made of ionized particles. It means the particle has electrons stripped from it, so it's no longer neutral. And these follow the sun's extended magnetic field lines. And there's one there on this one. That's ionized materials. There have been also comets that have sprouted multiple ion tails, which gives a stronger credence that it's following magnetic lines. And these do trace along the sun's magnetic field lines. And they have alternating plus minus charges, thus the ionized particles that are positive line up with the negative field, and ones the negative charges line up with the positive field. So you get these strands according to their opposites. So we have hydrogen cyanide, which is a negative ionized particle. We have potassium cyanide and sodium cyanide. These are cations. So we have both positive charge ions and negative charge ions. We've had several documented instances where comets have begun to sprout their tails millions of kilometers in deep space, well before the sun's heat, adding further credence that it's not a little dirty ice ball that's vaporizing. It's more magnetic, electromagnetic field phenomena. So anything volatile on its surface will show evidence of solar electrical field heating and interactions, and not heat. There's a picture of one here that actually has, again, 6 tails. And that was well past Jupiter. Depending on the comet's material, makeup, and eccentricity, or how elliptical it is, it can be classified as one of 3 types. There's short period comets. These generally last only a few hundred years before they break up when orbiting the sun. So the picture here is not real good. You'll see it better on your computer. And that's 153P Achaea. There's also long period comets. These have lifespans that theoretically range between 1,000 and 1,000,000 years, or several million years. There's an image there of one that's actually going around Saturn, and they theorize another dark star near us. Then there's the Jupiter short period comets, and these orbit between Jupiter and Mars, and they last anywhere from 20 to 40 years before coming from the Kuiper Belt, and they get trapped between the two. Got a streak of one here. That's Halley's Comet. And that's the end of